Thank you for joining us for today's presentation titled Safety in Field Metering Equipment. This presentation was prepared by Steve Hudson, Vice President of Hardware Engineering here at Powermetrix. Today we're going to cover what can go wrong when there is an electrical accident, how electricity damages the human body, safety standards used to protect electrical workers like you, and personal defense equipment that you can use to protect you from electrical accidents. Let's get started by showing a couple of real-life instances where things went wrong, resulting in an arc flash, and another incident where a hot stick is near the danger zone. All this leads to the big question. Let's look at what electricity does to the human body. But first, we must discuss how voltage and current interact to create danger. This brings up a theme in the discussion and one of the most fundamental equations in electricity, known as Ohm's Law. Voltage equals current times resistance. For the purposes of this presentation, however, we're going to rearrange that equation a little bit to make it current equals voltage divided by resistance. The more contact your body has with a circuit, the less resistance it presents. This table represents the various resistance levels of the human body. The thing we're going to learn is that the more current there is, the more potential damage can be done to your body. Researchers have looked into the resistance of the human body in various situations. For example, they have found that a dry finger touching a charged wire has between 40 kiloohms and 1 megaohm of resistance. If someone were to wrap their entire body around an electrical source, however, the entire body has between 200 and 1,000 ohms of resistance. In most situations, the voltage is going to be set at a constant value, so we can plug that number into the equation and begin to understand how things change. So let's look at the mathematics. In this example, we will assume the resistance of a hand holding a wire is approximately 10,000 ohms. In each location, then, we know the voltage and the resistance, so we can solve for the current and see what we're up against. Experiencing a shock at household outlet level should result in 12 milliamps of current. At the meter, you would expect between 12 and 48 milliamps of current. At the electrical pole, you would experience around 720 milliamps. And at the substation level, you're working around potentially 10 amps of current. With these levels in mind, let's see how much current it takes to affect muscle control, breathing, heartbeat, and tissue. At the household outlet where we found 12 milliamps of current, it takes only 3 to 10 milliamps to cause you to lose muscle control. Grabbing onto a wire at this level, for example, would trigger a grip reflex. You wouldn't be able to let go of the wire. At the meter site, where we expect to see 48 milliamps of current, it takes only 30 to 75 milliamps to stop your breathing. At the pole, where we expect to see 700 milliamps of current, it takes only 75 milliamps to 4 amps to stop your heart. At the substation, where you're working around more than 10 amps, Anything more than 4 amps will cause tissue burns. Now that we know what's at stake, let's look at the safety standards designed to protect you from harm. A safety standard is a document created by a group of industry experts. This document outlines the best practices for ensuring a product is safe to use. The folks tasked to create the IEC 61010 safety standards were required to determine the best way to protect you from hazards related to electrical shock, heat, mechanical stress, fire, mechanical hazards, and radiation. That safety standard has classified electrical hazards into categories. Category 2 represents the hazards you find at the electrical outlet level. Category 3 represents those found in circuits between the outlet and the meter. And Category 4 represents the hazards you will be dealing with most often at the meter to the lines at the pole. The highest safety rating a handheld meter testing device can have, according to IEC 61010, is Category 4, 600 volts. So what's the big deal? Well, it's important because when you're testing at a meter site, you are potentially part of the electrical circuit. If there's a sudden surge in the distribution lines, for example, if a lightning bolt strikes the line a couple of miles away from where you're tied into the meter with your handheld device, then you'd like that device to protect you from that massive surge in current, right? But when a surge does come into your PowerMaster 3 series device, where does all that extra current go if it's not being used to fry you? Again, using the Ohms Law equation of current equals voltage divided by resistance, our engineers can design a circuit that isolates you from that surge in a few ways. First, in the event of a lightning strike, a large portion of the surge will be shunted into the ground using overvoltage protection devices inside the PowerMaster. Under normal working conditions, the circuit already has a high resistance to minimize the amount of current that could reach you. And finally, isolation devices also provide a level of protection to prevent dangerous current from flowing through your body. Anything that might be left over is taken care of by the isolation provided by your gloves and boots. And speaking of personal protective equipment, let's review the equipment and standards used to protect you from electrical hazards. There's a lot of protective gear out there available to you. Let's start with gloves. ASTM standards provide a color chart to indicate the natural rubber insulating power of your gloves. Choose gloves based on the max use volume you could be working around. You also want to spend time each day or week inspecting your gloves for cracks, tears, and holes. Any place that is compromised can become a doorway for electrical power to enter. Can your safety glasses take a 1/4-inch steel ball flying at 102 miles per hour? Well, in the event of an arc flash where you can expect molten metals to be flying, you may appreciate having this level of protection. Not all hard hats are built the same. Look for the E and G ratings. Avoid the C rating, which is suited for construction but doesn't provide any protection from high voltage. Electricity wants to complete its circuit by traveling to ground. By wearing EH rated boots, designed to make the flow much harder, you reduce the likelihood of electrocution. And finally, what you wear matters when sparks and plasma fly. You're looking for shirts, pants, and overalls that indicate they are flame resistant and rated for arc flash protection. There are specific hazards meter technicians face every day. Although facing down that fearsome chihuahua on Wildwood Lane is sure to cause tears and anxiety for some of you, arc flash is actually one of the most dangerous situations a meter technician can face. But what is it? And how can you prevent it? Simply put, it's like a dam full of water bursting and rushing uncontrolled across the land. Except arc flash is so hot it melts metal and even reaches plasma states. You're most likely to see arc flash occur when removing a transformer-rated meter for testing. Be sure to engage the shunt bar of the CTs before you remove a meter. Ordinarily, the current flows through the meter at a low resistance. But when you remove the meter, the low resistance is replaced by high resistance, which produces a high voltage arc flash. By engaging the shunt bar, the current flows directly through the CT, providing a low resistance path. Meter sites with test switches can be used to bypass current through the meter so it can be safely removed. Hot sticks also represent a significant hazard area for meter technicians when using high voltage current probes and voltage probes to test CTs and PTs at the transmission and substation levels. Hot sticks work because they're basically giant resistors that prevent the flow of electricity down to the meter technician. Usually the hot stick doesn't provide electricity with an attractive route to ground, but if your hot stick has dirt, oil, grease, water, or any other contaminant on it, current may find a path through these substances. It pays to keep your hot stick clean. We love hearing from you. If you have any questions, comments, or stories to share, let us know by commenting below or by starting a conversation on Facebook, LinkedIn, or Twitter. Thanks for watching. Keep an eye out for future episodes of the Powermetrix Safety Series. Sign up for our newsletter to receive updates when we post new training materials on our website at www.powermetrix.com.